Bismillahir Rahmanir Rahim. This is our second lecture. In first lecture, we studied about the signal and its type. In first lecture, we studied that signal is anything that conveys information, or signal is a data set. So this value of signal can be real and it can also be complex. In complex to know and to deal with the complex signal, first of all we need to revise the complex number. So as we know that real number can be represented on one line. On one line we can, for example, 1 2 3 4, these are real number. So if this is 0, to the right of the 0 we have positive numbers 1 2 and 3 and so on, and to the left of the 0 we have negative number -1 -2 -3 and so on. But in case of complex number, the complex number cannot be represented by a single line. They are represented along a plane like this. In a complex number, we have two parts. One is called as a real part, and the one is imaginary. Like the here, we have if we represent a complex number by z, so z is equal to 1 plus j. 1 plus j. This is a complex number in which the real part, one is real part, one is real, and j represent the imaginary part. Here its value is also 1, so this is the imaginary part of the complex number. So to represent this number along a plane, for example, this is our plane, this is the real axis and this is the imaginary. Y-axis is termed as imaginary and x-axis is known as the real axis. So we need to plot this number z. So move to the on the real axis 1 unit and 1 unit on the imaginary axis. So this is the number. This is the number. This is 1 plus j. So this is how we represent a complex number in the in a plane. And this representation is the one I have represented. Like here we have the example of 3j plus 2. This is plotted over here. See this one. So this representation of the complex number is named as Cartesian, or the rectangular representation. This term representation is named as Cartesian or rectangular representation. I have mentioned it over here. Now as we know that complex number can also be represented by a vector, and the vector representation of the complex number is named as polar representation. For polar representation we need two values. One is vector length, also named as magnitude, and the one another one is the angle of the vector with the real axis, called as angle. Like here, one is the vector length or magnitude of the vector, and second one is the angle it does makes with the real axis. This length, this is the magnitude, and the angle. We need these two to represent the complex number in polar form. We can convert the complex number from rectangular form to the polar form. in rectangular form we need the real part and the imaginary part, x and y. However, in case of the polar form we need the magnitude and the angle. So if we are given with the real and imaginary part, and to calculate the magnitude and the angle, here is the formula: m is equal to under the root x square plus y square. X is real value, y is the imaginary value. Theta is equal to tangent inverse y by x. And to represent this in the polar form, this is magnitude and this is the angle. This is the polar representation of the complex number. And in case if we are given with the polar representation, and to convert it to the Cartesian, we need this formula: x is equal to x is equal to m cos theta and y is equal to m sin theta, and we will have the values of x and y, and here is the rectangular representation of the complex number. Okay, this angle theta, in case of the polar representation, this angle theta, to represent this theta, it can be represented in degrees or in radians. For example, if this is the a complex plane, this complete rotation is 360, or it is 2 pi radian. This complete rotation is 2 pi radian or 360 degrees. If a vector lies over here in the mid of the x and y, this is 45 degrees or pi by 4 radians. So what is a radian? 1 radian is equal 1 radian is defined as, if let me draw over here, if this arc, this is an arc, if the length or the circumference of this arc, this is equal to the radius of the arc, or the radius, if this length is equal to this length, if length and circumference of the arc is equal to the radius of the arc, then this angle, this vector making with the real axis, it will be equal to 1 radian. This will be equal to 1 radian. Okay, and 1 radian is equal to 360 divided by 2 pi. If, for example, if this arc is like this, here, this arc is moving like this here, so it completes 2 pi radian. 2 pi radian. So 2 pi is equal to 360, pi is equal to 180 degree, pi by 2 90 degree, pi by 4 45 degree, pi by 3 60 degree. Okay, another thing we have, if the magnitude is 1 and the angle is theta, so to convert it into the real and imaginary part, we can write like this: 1 cos theta plus j sin theta, like I have written it over here. And we know by the Euler formula that this cos theta plus j sin theta is equal to e power j theta. Do think over it, and you will know from your previous courses that this is the Euler formula. We can write this like this: e power j theta is equal to cos theta plus j sin theta. This is the real part, this is the imaginary part. So we have three type of representation for complex number. This one is the polar representation or magnitude and angle representation, real and imaginary representation or rectangular representation, and this one is the exponential form of the complex number. Exponential, this representation of complex number can be named as exponential form. This can be named as exponential form. So we can write 1 theta as 1 e power j theta, 2, if the 2 is magnitude and theta is the angle of a complex number, we can write this in term of exponential form as 2 e power j theta. And if the magnitude is 3, angle is pi by 4, we can write this in term of exponential form as 3 e power j pi by 4. So we have three types of the complex number representation. This one is the rectangular representation or rectangular form, a real imaginary form or Cartesian form. This form m and angle theta, this is polar form or magnitude phase form, and this form m e power j theta, this is the exponential form of the complex number. Okay, to represent e power j theta or to plot e power j theta, here its amplitude is or magnitude is 1, so a vector of unit 1, and this vector is making angle theta with the real axis. This is the plot of this e power j theta. J pi by 2, so its magnitude is 1 and angle is 90, so it will be, this is the 90 angle pi by 2, so this is the plot of the this e j pi by 2. And here also we can convert it in the real and imaginary parts. Cos pi by 2 plus j sin pi by 2, cos pi by 2 is 0 and j pi by sin pi by 2 is 1, so it's equal to j and j, 1j. So over the y axis we have j. So similarly here we have some question how to plot ej pi, how to plot e to the power j0, how we plot ej 2 pi, and how to plot ej 2 pi k. K is any integer. This is your practice, and do practice how do you plot these exponent or the phase. So if I plot e power j pi, so magnitude is 1 and angle is pi, so this is 0, this is pi by 2, and here it is pi, so this is unit 1 and this is ej pi. This is the plot of the ej pi. This is 180 or this is pi. Is it clear? And how to plot e power j0, magnitude is 1 and angle is 0. How to plot ej 2 pi, magnitude is 1, so this is 0 and 2 pi radian, again this is 2 pi, so the plot for 2 pi is same. And for any integer 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, all will have the same same plot like this. So here to revise some the arithmetic operation of the complex numbers. So how do we add the two complex numbers? Add the real part and the imaginary part separately. To multiply two complex number, the best thing is to convert it into the exponent form, like this and like this. One is m e j theta and the another one is n e power j phi. So the magnitude will be multiplied and the angle theta plus phi will be added. For example, if we take example, one complex number is e to the power j pi by 4. This is the plot, and another one is e j pi by 2. This is the plot. If both are multiplied, so we get e j common, pi by 4 plus pi by 2, and this is e power j3 by 4, and this is the plot. If we need to plot a number 3, like 3, so 3 is a real number. 3 is a real number. So it can be it will lie on the real axis, like here, 3. And if we multiply a complex exponential with the 3, and that a 3 exponential is e to the j pi by 2, so what we'll do, this phasor will be rotated to the pi by 2. First it was lying over here. After being multiplied with the pi by 2, this phasor will be rotated to the pi by 2. Its angle will change. So angle will change from 0 to pi by 2. Its angle will be changed from 0 to pi by 2, like here. So when a number is being multiplied by a complex number, there is rotation. There is rotation based on the complex number. Like here we multiplied 3 by e to the j pi by 2. So the angle will be added. So angle will be added, or this complex this phasor is rotated. This is rotated. Okay. So this was all about the complex number. Now let's move a step forward. The complex exponential signal. Complex exponential signal. So what is a complex exponential signal? Any signal written in exponent form. Any signal written in exponent form, like this: e to t, e to j, 3 pi t. These all are the exponential signal. It can be written in the exponent form. So before going to that, let us see that e j theta. Here theta is a fixed number. So this is the complex exponential form of complex number, e j theta. This is the complex exponential form of complex number because theta is fixed. It's not changing. And if theta is changing, theta t, what does it mean? That theta, the angle, does change with the time. As the time t changes, if we plot theta t across, this is the angle theta t, and this is time t. So this theta t does changes with respect to time. It does increases like this, linearly changes. As the time t increases, theta t does increase. So in this case, we call the signal as the complex exponential signal, e j theta t. And what is theta t? Theta t is equal to omega t. Omega theta t is equal to omega t here. So we can say that x of t is equal to e power j omega t. x of t is equal to e power j omega t. Now omega is a fixed number, for example any number. So depending this exponential signal e power j omega t, it will rotate on the complex plane. This is a complex plane, this is the real axis, this is the imaginary axis. We call this plane as the complex plane because it has a real part as well as imaginary part. This is the positive imaginary, this is negative imaginary, this is positive real, this is negative real. So this complex exponential signal will rotate on this complex plane depending on the value of omega. Based on this omega, it will rotate on this complex plane. Based on this, it will rotate like this. For example, if I plot e power j 2 pi, let me plot e power let me plot e power j pi by 4. G pi by 4 is 45. So to plot this on the complex plane, this is real axis, this is imaginary axis. To plot this, we have one vector or one phasor over here, and the phase is pi by, our angle is pi by 4. Now if this is a complex. Now if we have e j pi by 4 t, now e j pi by 4 is something different and e j pi by 4 t something different. So let me plot this. At t is equal to 0, at t is equal to 0, this will be over here. At t, as the t changes, this phasor will move on like this. If t is equal to 1, it will be here, and as the t value changes, it will rotate like this. This phasor will be rotating like this, and as the t value changes, it will does rotate on this plane like this. I think you are getting my point, what I am saying. If this is t is not here, this is a fixed value, and if this t is here, so this is not a fixed value, but it is does depending on the value of t. As the t value changes, it will, this phasor will does rotate on the complex plane like this. This is what does I mean from this sentence. It will rotate on complex plane depending on w. In our example, w value was equal to pi by 4. It was equal to pi by 4, and this w is, we will study what is w. So, but at the instant, do consider that this w is some constant number, and depending on the value of the w, this complex signal or the phasor will rotate over the complex plane. And if you consider another important thing, that this complex exponential signal is rotating on the complex plane like this. One rotation, second rotation, third rotation, and so on. So if you consider, it is repeating itself after some time. It is repeating after some time. This is what we defined the periodic signal. Alhamdulillah. So we can say that the is a complex exponential signal is a periodic signal because it is repeating itself after regular interval. For periodicity, we defined that a signal is periodic if xt is equal to xt plus capital T, and this capital T is the period of the signal after which it repeat itself. So this T is the period of the signal. So if e j omega t is periodic, so it means that it must be equal to e power j omega t plus capital T. And we can write this like e power j omega t, e power j omega capital T. To be periodic, this e power j omega t must be equal to 1. And let us see that when it equal to 1, e power j omega t is equal to 1 when omega t is equal to 0, e power j 0 is equal to 1, or it is equal to omega t is equal to 2 pi, e power j 2 pi t, this is also equal to 1, or this omega is equal to 2 pi k, any integer multiple of 2 pi. So based on that, so for any of these values of omega t, if omega t is equal to 0, 2 pi k, this e j omega t is equal to 1. So what is t? T is period which is smallest positive value as per the definition. So to find, if we say that the smallest positive value, so what will be the smallest positive value when omega t is equal to 2 pi? This is the smallest positive value. And to find the time period, t is equal to 2 pi by omega. If we consider omega t is equal to 0, so t is equal to t will be equal to 0 by omega, which is undefined, so that is not the case. That is not the case. Omega t must be equal to 2 pi, and t is equal to 2 pi by omega, and t is the period. This is period. Like here. So what does period mean? That one cycle in 2 pi by omega second, 2 pi omega second, or t is equal to 1 over f is equal to 1 over t, so frequency is equal to omega divided by 2 pi. What does it mean? That omega divided by 2 by pi cycle in 1 second. For example, this is the phasor and it is moving on this complex plane. So the time period will show that how much time does it take this phasor to complete one cycle, and the frequency does shows that how many cycles does it complete in 1 second. Think over it. It's very simple but very important. Next, for example, if we have a complex signal like this, xt is equal to e power j 4 pi t, omega is equal to 4 pi. Now to calculate the time period, t is equal to 2 pi by omega or 2 pi by 4 pi, so t is equal to half second. What does it mean? It means that this phasor will complete one rotation in half second. It will take 1 second to complete one rotation. And if we calculate the frequency, so we know that f is equal to omega divided by 2 pi. omega is equal to 4 pi, so 4 pi divided by 2 pi, so equal to pi cancel, so f is equal to 2 cycle per second. What does it mean? That this signal will make 2 cycle, or this phasor will complete 2 cycles in 1 second. In 1 second it will complete 2 cycles. According to this, so if this phasor is completing 1 cycle in half second, so it has moved 360 degree, and in another half second it complete another cycle, so a total of 720 degrees it is moved. Or if we see the radian, so in half second this phasor completed 2 pi, and in half second it completed 2 pi more, so in 1 second it did completed 4 pi radian in 1 second. So omega is equal to 2 pi f. Omega is named as angular frequency and f is the frequency. So the value of omega will show that how fast this phasor will be moving on a complex plane. Again, see over here, ej theta, this is the exponential form of the complex number. It is equal to, according to from Euler formula, we know that this is equal to cos theta and j sin theta. This is the real part, this is the imaginary part. If we consider the complex signal ej omega t, it will be equal to cos omega t and j sin omega t. This is the real part, this is the imaginary part. So to plot this signal, ej omega t, we will be not having a single plot, we will be having 2 plot. If we plot in a real and imaginary, or we can plot this signal ej omega t in 3 different ways. Number 1 is real and imaginary part. This is the one method. Second method is the magnitude and phase. Not phase is not phase or angle. And the third method is the exponential method, or the complex complex plane. So this signal ej omega t, this is the real part, cos omega t, this is the sine, this is the imaginary part. So this signal has 2 plot. One is real, this is the real part of this signal, this is the imaginary part of the signal. And if we find the magnitude and the angle of this signal, so plot the magnitude. For example, if its magnitude is 1 and its angle is say 2 pi, so magnitude 1, so this is 0, this is time t, so its magnitude is 1, means for all t its magnitude is 1. This is 1, this is the plot. For phase, say its phase is 2 pi, so 0, at 0 its phase is 2 pi. Again it does increases, at 1 it become 2 pi, and it will move on at 4, sorry, at 2 it will be 4 pi, and at 3 it will be 6 pi. But we know that 4 pi is also equal to 2 pi, 6 pi is equal to 2 pi, and 2 pi is equal to 0. So we can plot this as like this: 0, 1, 2. So for 0 it is 0, for 1 it is 0, for 2 it is again 0. So 2 pi is equal to, phase of 2 pi is equal to 0 phase, equal to 4 pi, equal to 6 pi. For integer multiple of 2 pi, it is equal to this. So this is the phase plot, this one. And exponent form e power j omega t. This is the magnitude of the phasor, and this phasor is moving over this complex plane depending on the value of the omega. What is the value of the omega? It will move on at this plane. Now next we have one another important thing, harmonics. What are harmonics? For example, if we have a complex exponential signal xt equal to e j omega t, and we have another signal xt equal to e power j k omega t, k is any integer, means that, so let me change the name to y of t. Xt is equal to e power j omega t and y of t is equal to e power j k omega t, where k is the integer plus minus 1 plus minus 2 plus minus 3, means that its frequency is the integer multiple of xt. The frequency of the y of t is the integer multiple of xt. So these type of signals which whose frequency are integer multiple of each other are named as harmonics. The signals, like here, signal whose frequency are integer multiple of each other, these signal are named as harmonics. Harmonics are the periodic exponentials, all of which are periodic with common period t naught, whose period is t naught, has a same time period. Frequency may be changed, but it has the time period, same common time period. These are called as harmonics. So like this, see over here, e j theta, this is the fundamental frequency. For example, omega, fundamental omega naught is equal to pi by 3. Now omega 1 means k is equal to 1, equal to this one 2 pi by 3. Omega sorry, this is omega, this is omega naught or omega 1, this is omega 2, omega 3 equal to pi, omega 4 is equal to 4 pi by 3, and so on. So these are the harmonics. Harmonics are harmonically related signal. So this is all about the complex signal and the basics of the complex exponential signal. In next lecture we will study the complex exponential signal, real exponential signal, the imaginary exponential signal, and general form of the complex exponential signal. You are requested to please watch these lectures, and if you have any queries, please let me know. We will also have the online session, so if you have any question, we will answer that at that specific time. Thank you.